This conference will now be recorded.
Hello everyone. So here we will discuss previous year's questions from JEE Advanced exam, and that is from the chapters Basic Principles of Organic Chemistry. Here we have the first question. Match the reactions in list 1 with the features of their products in list 2. Okay, so in list 1 you can see there are total 4 reactions, P, Q, R and S. And in the right hand side, that is list 2, 1, 2, 3, 4, 5. Total 5 types of products with their features are mentioned. That means one may be extra, one item may be extra. So here we have the first compound which is mentioned as single enantiomer, and it is 1-bromo 2-ethyl pentane. So if we draw the structure for the first reaction, this is pentane. At one position there is bromine. This is 1, 2, 3, 4, 5. And at two position there is ethyl group. So you can understand this is the chiral center present. The chiral center is not that carbon with which bromine is attached. Now when you are treating it with HO minus, that is you are treating it with aqueous NaOH, and there is SN2 reaction, this HO minus, it will attack at this carbon which is bearing the leaving group Br, and Br will be substituted by HO. But you have to be careful that their chiral center is not disturbed here. It is still intact. That means the attack at this carbon is occurring. At number 1 carbon, attack is occurring. But that has nothing to do with chirality. So here question of inversion, or that is question of inversion, which normally happens in case of SN2, that question does not arise. So here retention will be present. That means it is matching with this, that is P is matching with 2. What about the next one? In the next one, which is Q, here also we have single enantiomer 2-bromo-pentane. So we will draw the structure first. 2-bromo-pentane. So this is the chiral center where bromine is attached, and it is again treated with NaOH. That means HO minus hydroxide ion is the attacking ion. This is also SN2. Now when it will attack here, if initially it is R isomer, it will be converted to S or vice versa. That means here inversion will take place. That means it is matching with this one. Okay. Now come to the next one, which is R. In R also we have single enantiomer, and we are attacking with NaOH, again same reagent, but now the reaction is SN1. We will draw the structure here. 3-bromo 3-methyl hexane. So this is hexane. At 3 position there is bromine, and at 3 position there is methyl group also. So this is the chiral center present in the molecule, and when you are treating it with HO minus, we know in case of SN1, initial whatever configuration we have, suppose you have this enantiomer as R form or S form, these are the two possibilities. But when you are starting with R, then also you will get some racemic mixture. When you are starting from S, then also you will get some racemic mixture, because the attack of these HO minus from both sides of the carbocation, because in SN1 reaction there is generation of carbocation like this, that is after bromine removal, the methyl group is here, we will have some carbocation, and the HO minus, it can attack from both sides. This carbocation is planar, so that is the reason we get mixture of enantiomers. That means it is matching with this, that is number 3. And what about the last one? In last one, the molecule is already drawn, and if you watch carefully, this is chiral center, this is also chiral center. But when you are attacking with hydroxide ion, this hydroxide ion will attack at the carbon where bromine is present. Now at this center, that is the second chiral center where bromine is present, SN1 reaction is mechanism is going on. So here there will be change of configuration. That means initially if it is R, you will get mixture of R and S. Initially if it is R, then initially if it is S, then also you will get mixture of R plus S. But see, here this chiral center is not disturbed at all. There is no change. That means this will remain fixed. Only the racemic mixture is happening at this position where the actual reaction is happening. So that means when one chiral center is fixed, but another chiral center is changed, you are getting both R and S. Then what will happen? You will get some diastereomeric mixture, because what we know, when you have more than two chiral center and only that is one chiral center is still same, but another chiral center is changing, then what will happen? Then there will be formation of diastereomers. So that is why we will now get mixture of diastereomers. So it is matching with 5. Now here it is matching with option B. But one suggestion also I can give you. See, in option B, S is matching with 5, and okay, this is also present in D. So based on that, you cannot do anything. So I'm just trying to find out whether there is anything exclusive, that is anything unique present in option B, so that directly you can choose. So here one thing is present, that is Q is matching with 1, which you will not get in any other options. Okay, so that is inversion. Q is matching with 1, that you will not get from any option. So based on that also you can choose this answer. But we have now all the explanations why we are choosing option B as the correct option. We will go to the next one. Here, this is basically paragraph based question. So some informations are given in this paragraph along with 4 reactions with some data. And based on this paragraph, there will be 2 questions. So this is the format that we get in JEE Advanced exam. So read this paragraph carefully. The amount of energy required to break a bond is same as the amount of energy released when the same bond is formed. Suppose you are forming a bond AB, okay, or you are breaking the bond AB. So when you are breaking it, obviously you have to supply some energy. Suppose you are supplying 30 kilocalorie. I am just saying arbitrarily. Suppose you are supplying 30 kilocalorie energy, you are supplying to break this bond. Now when A and B, this bond will be formed from A dot and B dot. That means from radical, when this bond will be formed, then some energy will be released. This is exothermic process. And what amount of energy will be released? The same amount. Now the sign will be just negative because now it is exothermic. So this is the meaning of the first statement. Now in gaseous state, the energy required for homolytic cleavage of a bond is called bond dissociation energy, in short BDE. It is also the indicator of bond strength. Now homolytic cleavage means when both the electrons, that is not going to the same atom, this one electron is going to A, another electron is going to B. So that is why it is homolytic cleavage. Now bond dissociation energy is affected by S character of the bond. So higher is the S character of this bond, higher will be, that is more energy you have to spend. And also the bond dissociation energy depends on the stability of radicals. Suppose when you are breaking the bond A and the bond between AB, you are getting A dot and B dot. Now if these radicals are very stable, obviously now the bond dissociation energy will not be very high. You can easily break this bond, right? But if S character of this bond is very high, S character means suppose you are breaking a bond which is, see, this carbon is sp hybridized. So when you are breaking this bond, it will not be very easy. Okay, so that is the meaning of this line. Then we also have some more informations. Shorter bonds are typically stronger bonds. So when bond length is less, bond strength will be high. And here you can see some informations are given. We are breaking the bond CH3 and H. That means if you have methane molecule, if you are breaking one of the carbon hydrogen bond, you will get these 2 radicals. And here this amount of energy you have to supply. When you are breaking the bond between 2 chlorine in chlorine gas, then you are getting 2 chloride dot radical. You have to supply this amount of energy. Then when you are breaking the carbon chlorine bond in methyl chloride, you are supplying 85 kilocalorie per mole. And when you are breaking the bond between H and Cl in hydrochloric acid, then you are supplying this amount of energy. Okay, so all these are positive because you have to supply energy. So this is the information given. Next we will discuss 2 problems based on this paragraph. So this is the first problem. Here whatever information you are seeing in the previous slide, that is related to these reactions, that you don't have to use here. It is completely different problem. But the second problem, you have to use these data. So that is why these data are given. So here you can see in first column, here we have some molecules P, Q, R, S. These hydrogens are bold. Why? Because you have to focus on this carbon hydrogen bond in each of these molecules. And you have some bond dissociation energy in unit kilocalorie per mole given in second column K. So you have to match this. Okay. Now when you are breaking in first case, what radical you will get? You will get this type of radical, right? When you are breaking the bond in PHCH3 basically, toluene, what you will get? You will get PHCH2. This is the radical. Now for R and S, basically in this case you are having some CC double bond and CC triple bond. That means in case of R, this carbon is sp2 hybridized. And in the last case, the carbon hydrogen bond that you are going to break, that is actually the carbon is sp hybridized, right? Now based on this, and for the first two cases, both are sp3. So if I consider, that is if I give the explanation on the basis of S character, now obviously in case of R and S, you have to supply more energy, right? And in which case you have to supply maximum energy? That is for last one, because here you have S character, where S character is 50% because it is sp hybridized. So here you have to supply maximum amount of energy, which is 132. That means S is matching with 1. Now if S is matching with 1, then this is the maximum energy 132. The next maximum is 110. So this must be 110 because it is now having some lesser S character compared to this molecule. But compared to P and Q, it is you have to supply more energy. So that is why it is 110. Fine. Now if it is 110, that means Q is matching with, sorry, R is matching with 2. R is matching with 2. Okay, so R is matching with 2, S is 1. Now just this information is enough to choose the correct option, which is first, isn't it? Actually, if you are sure that S will be matching with 1, that is S is associated with 132 kilocalorie, the maximum energy, then also you will be able to choose the correct answer. Okay, now we will also see why P and Q are having 3 and 4. So P is basically here 3. That means you have to supply 95, and in this case you have to supply lowest amount of energy. Now why it is so? See, here you have to consider stability, because based on S character you can't do anything. In both cases same hybridization, S character same. But based on radical stability you can do something. Here radical is more stable. Why? Because we have pH ring. So if I am writing the structure like this single electron, it can undergo resonance with the double bonds of the benzene ring. But here that type of resonance is not possible. It is true that hyperconjugation is possible, but this factor is overcoming. So that is why Q should match with 4. So that is why P is 3. Option A will be the correct option. Okay. Now we will go to the next question based on the same paragraph. Now you can see these informations you will need. as you can see here, we have four informations given, and based on the bond breaking energy and bond formation energy, we have to solve this problem. So let's see one by one. Here the first statement is saying that initiation step is exothermic with del H value minus 58. Now what is initiation step for this reaction? This is the overall reaction where one of the carbon hydrogen bond is replaced by carbon chlorine bond. Fine, and the byproduct is HCl. So here you have to understand all these steps for this reaction. So in chain initiation, basically you have to break chlorine-chlorine bond. Now to break chlorine-chlorine bond, you have to supply this amount of energy. It cannot be exothermic. You have to supply energy. So this is not correct statement. Come to the next one. Propagation step involving CH3 dot formation. So propagation step may be two types. This is number one propagation step. This is number two. So in the first propagation step, you are breaking carbon hydrogen bond. So to break the carbon hydrogen bond, obviously you have to use energy. Which energy? You have to use this energy, that is to break carbon hydrogen, okay, this energy you have to use. So for B, you have to supply plus 105, but in this case Cl dot is also generated. That means along with this 105, this 103 amount of energy will be released, because here HCl is also formed. That means HCl bond formation energy, if you consider, this amount of energy will be released. So ultimately what you are getting plus 2 kilocalorie, and it is not exothermic. You have to provide this energy. So that is why this is also incorrect. What about C? Propagation step involving CH3Cl formation. Now CH3Cl formation is the second propagation step where you are breaking chlorine-chlorine bond. Now to break chlorine-chlorine bond, you have to supply plus 58 energy, and this bond is formed. That means this amount of energy will be released. Now if you take the summation of this, it will be minus 27, but here it is mentioned plus 27. So this is again incorrect. You are left with only one option. That will be obviously correct, but why it is correct, that we have to see. So here overall reaction, if you consider in CH4, basically here CH3Cl bond is formed, and HCl, the bond between H and Cl is formed. Now which bond is breaking? First we have to consider. So breaking, I am writing here B, and formation I am writing here F. So breaking means you have to supply this energy, and formation means this amount of energy will be released. So for breaking, which bond is broken here? 105 and also 58, because you are breaking Cl. So for breaking, you have to supply this amount of energy, which is basically, okay, let me write the other one. Now which bonds are formed? The bond between chlorine carbon, that means 85 amount of energy released. So under released I am writing 85, and also 103, this amount of energy released, but I am taking common, so ultimately it will be like this. Now if you do the calculation, you will see you will get minus 25. That means overall the reaction is exothermic. That means this reaction is that is the last option is basically the correct option. Okay, so it is a very good question, because from if you can solve this problem, so many things you will be able to know from this by solving this single problem. We'll go to the next one. Here we have Fischer projection of D-erythrose, and that is the picture is given. Now D-erythrose and its and its isomers are listed as PQRS in column 1, and choose the correct relationship of PQRS each time with D-erythrose, the relationships given in column 2. So three different types of relationships are possible, as you can see, but which relationship will be correct, that we have to match. So what we will do first, we will see, we will find out the nomenclature. So that is the way I will follow here, but if you want to do it in a different way, that also you can do. So what is the different way? The different way is each time you can convert this to some Fischer projection. For PQRS. So total 4 Fisher projection you have to draw. That is one method you can follow. But what method I am following here is I will find out the RS configuration for these two chiral center. So these two are the chiral center. So for the first carbon, that is this where CHO is attached. So this will be number 1 priority, this will be number 2 priority, hydrogen is obviously lowest, and this total group that will be number 3 priority. Okay, and when you are moving from 1 to 2 to 3, basically it is anti-clockwise, that means it is R. And the same way, let me erase all this because I will now decide for the second chiral center. Now this will be 1, this total group it will be 2. Okay, because why? With this chiral center, the next carbon it is attached to HCO, but this carbon is attached to 2 hydrogen and 1 oxygen. So that is why it is winning over this group. So 1 to 2 to 3, if you are moving again anti, that means this is also R. Okay, so now we know the molecule given D-erythros, it is RR configuration. Now check the PQRS one by one. So for the first center, if we see, this is anti-clockwise and hydrogen is away from us. That means it will be R. What about the next one? It is 1, this group is 2, 1 to 2 to 3. So again we are moving anti-clockwise, but H is towards us. That means it will also be R. So RR, that means it is identical. So P must be identical. That means P is matching with 2. Now P is 2 present in option 1, 3, 4. So it will not help us. Go to the second one. In this case, it is just reverse of this first configuration as you can see in P. So that is why now see it is clockwise, but H is towards us. So that is why after all it will be S. What about the second chiral center? It is moving in this direction. That means it is moving clockwise and H is away from us. So it will be R. So S and R, that means Q is matching with diastereomeric relationship, which is 1. So if P is 2, R is 1. Sorry, P is 2, Q is 1. That you can find in this option. Okay. So we will also check the other two. R, in case of R, OH to CHO2. Actually, you don't have to do it again and again because see, in case of P, this center and these two are same. So again, it will be R. Okay. You can also do it, but for saving time, I am just doing in this way. So 1, 2, 2, 2, 3, H is away from us. It is anti-clockwise. That means it will be S. So S, R, S. Again, it is diastereomeric. That means R is also 1. So it is still matching with option 3. What about the last one? OH to CHO to this group, but it is clockwise, but H is towards us. So that is why ultimately it will be S. And the same we will do for this. This is one group. This total group is 2. This is 3. CH2H is 3. So 1 to 2 to 3 we are moving clockwise, but H is towards us. So that is why it will be S. So RR, this is SS. That means the last compound is basically enantiomeric relationship. That means it is 3. So everything is matching with 2. Sorry, option 3. But see, until if you can move until this point, then also you can choose option 3 because P2Q1 that you can get only in option 3. Okay. So even you don't have to solve R and S. Okay. So next problem. Total number of isomers considering both structural also stereoisomers of cyclic ethers. Molecular formula given C4H8O. Cyclic ether. Okay. So C4H8, that means the maximum number of carbon that we can get. Sorry, it is not C4, it will be C5. Sorry, there is a mistake. Okay. So maximum number of, that is a, sorry, it is fine. Actually, it is C4. We will start with, it is cyclic ether. That means maximum ring size can be 5. So when ring size is 5, that means under this condition you can have only this structure. Okay, you cannot have more than that. Total 4 carbon, 8 hydrogen, 1 oxygen. Now when ring size is 4, under this condition what you can get? You can get this type of structure, but one methyl substituent you have to place. But methyl substituent can also be placed at this position, isn't it? Now first I will draw all the, that is I will overlook the stereoisomerism. I will simply draw the structural, all the probable structures. When ring member is 3, under this condition, now 2 carbon, another 2 carbon you have to place. Suppose I am putting a ethyl group here. Next possibility is, if I am putting both the methyl group here, third possibility is also there. If you are putting it like this, now you have to consider. So these are the maximum possibilities under structure. But you also have to consider the chiral center present or not. So here we have chiral center, isn't it? The next 4-membered ring, here sigma, this you can cut the molecule along this line. So when sigma plane is present, it is not chiral. Next, in case of 3-membered ring, this is chiral center. That means here R and S, these two configurations are possible. Next we have this one. It is not chiral center. That I am talking about, this is not chiral center because you have two same groups. So RS is not possible. Now the last one is very interesting. Here you have two chiral center, and when you have two chiral center, according to the formula 2 to the power 2, total 4 possibilities are there. But see, if we consider all the 4 possibilities, it is basically RR, SS, RS and SR. But ultimately you will see these two will give you, that is RS and SR, these two will give you mesostructure. So ultimately you will get total 3 from this. So considering this, here we are getting 1, here we are getting total 3, here we are getting 1, 2, 3 and 3, 6. So 1 plus 3 plus 6, it will be total 10. So here everything is mentioned, how we are getting total 10. It is integer type of problem. Now, if I go into the details, answer is 10, that is fine. But it is clear for all. But this one, if I explain it a little bit, these are the possibilities where both the methyl groups, they are above the plane. This is one possibility. Another possibility is when both the methyl group below the plane. Okay. Now when you will see above the plane, you will find it as R and S. And when it is both the methyl group, sorry, it is R. Both the methyl group are, okay, let me check it once more. So here see, this will be hydrogen is already away from us. So this will be number 3 priority. This will be number 1 priority. That is this bond, and this will be number 2. So when you are moving 1 to 2 to 3, it is basically R configuration. Similarly, if you consider this one, you are now moving anti-clockwise. Okay. So this will be S. Similarly, for the next one, this will be S and this will be R. As if we have just reversed it. But these two molecules, if you see, there is a plane of symmetry, isn't it? So that is why you can cut the molecule. So after all, these two molecules will be meso. So you will get just one configuration from it. But if you consider the trans, these two are actually Cs. Both these are Cs. But see, if you consider trans, now this side will be R, this side will be S. Fine. Similarly, if you consider another trans, now you will see this side will be S and this side will be, this is R these two will be SS. So when it is RR and SS, these two are actually enantiomer. That is, from the trans you will get two structures. Okay, so that is the reason why we are getting ultimately total 3 we have to consider. RR, SS, number 1, number 2, and RS. Because RS and S are both are after all same. If you simply invert the molecule, you will get the same structure. So answer is 10. Next question. Choose the correct option or options. More than one answer can be correct that give or gives aromatic compound as the major product. Here we have taken NaOET. Now this is basically base. What kind of base? Here ETO minus can capture hydrogen. So what it will do? It will capture this hydrogen and ultimately this CH bond will be broken. CBr bond will also be broken. You will be getting species like this. Now is this aromatic? Because we have to find aromatic compound product or not. This is not aromatic. This is basically anti-aromatic because here total number of electron 4 pi electrons. The conditions for aromaticity, it must be cyclic. There must be a full conjugation. That is, in the whole ring there should be conjugation. Then it must be planar. And the last rule to maintain aromaticity is 4n plus 2. But it is not matching with the last one. Rest of the 3 are fine. So that is why this is not correct. That is, it will not give us anything aromatic. What about this one? Now here you have 2 bromine, and with respect to this bromine, this is alpha position, this is beta position. At beta position you have hydrogen. Similarly, with respect to this bromine, again you will have alpha position and beta. That means 2 times you can remove HBr, and 2 different types of base are given. So when you are using KOH, then one HBr will be removed and you will be getting structure something like this. Okay, now you already have CC double bond. You have to remove one more HBr. Now to remove the second HBr, you need a stronger base compared to the previous situation. So that is why NaNH2, sodium amide, is even stronger than hydroxide base. So when you are using it, another HBr will be removed and ultimately you will get this type of, basically it is, I should write it like this because it is linear. This is CH3, this is carbon, and this is CH. So we are getting this molecule CH3 CC triple bond H. Next reagent is red hot iron tube. We know when you take simply acetylene, 3 acetylene molecule together can make benzene under the same condition. But you are starting with methyl substituted acetylene. So ultimately in the structure, you will have 3 methyl. But after all, this molecule is aromatic. This is benzene. So this should be our correct option. What about C? When you are using excess chlorine, under this condition, UV, very high temperature, basically all these CC double bonds will be broken. You will be getting product something like this, where all the positions there will be Cl. Total 6 chlorine will be there. But aromaticity is lost. So this is not correct answer. Last one. ONE is basically the base, methoxide. And this will capture this hydrogen. As a result, there will be negative charge. Now this molecule is aromatic. This anion is basically aromatic because total 4n plus 2 rule, if you considering this electron, total 6 pi electrons are there. This electron can take part in resonance, total 6 pi electron, where n value is 1. So all the conditions for aromaticity fulfilled, and that is the reason D will also give you aromatic product as the major product. Here it is mentioned major product because sometimes some other byproducts you may get, but that you don't have to consider. Just focus on the major product, whether it is aromatic or not. So these two are the correct options, B and D. For the given compound X, here we have a structure given. You have to find total number of optically active stereoisomers. Not just stereoisomers, that has to be optically active because mere presence of chiral center, it doesn't make a molecule that is chiral, that is, it doesn't make the molecule optically active. because meso compounds also there is chiral center, but it is not optically active because of the presence of sigma plane. So you have to be careful that whether it is actually optically active or not. Now in this molecule, two informations are given. For this type of bond, it means configuration at the specific carbon. That means this carbon, this carbon, this and this. These four positions. You have this type of bond. It means that the configuration at the specific carbon. That means here chiral center is fixed. It is not that it will be either a R or either or S. It is not that mixture of RS. And also the geometry of the double bond is fixed. That means this geometry, here you can see it is E geometry, isn't it? So this geometry is fixed here. You cannot change it. But when you have this type of wavy bond, it indicates configuration at this carbon and also the double bond. That means this configuration, and this one, these three are not fixed. This is the difference. Now if we apply this rule, here we have two chiral center, and from the CC double bond also you can get E or Z, two types of geometrical isomerism. So that is why, as if there is total 3 chiral center. So that is why 2 to the power 3. So it will give you total 8 stereoisomer. But among these 8 isomers, you have to check whether there is any meso or not. Because if there is meso present, that you have to subtract. Because after all, you have to find only the optically active, not just any stereoisomer of this molecule. Okay. So in this picture, you can see this CC double bond is fixed. We cannot change it. But the second CC double bond, here in all cases, it is E. So if you fix this condition, that this CC double bond is E, you can have 4 possibilities. See, this is above the plane, below the plane, above the plane, below, above, below. So these are the 4 possibilities. But is there any meso compound? Yes. If you cut this molecule along this line, both half are as if mirror image to each other. That means both half are equal, symmetrical. So these you have to reject. But when, so these 4 are when you have fixed the CC double bond configuration E. But when it is Z, again you can have 4 possibilities. See, all these are Z. So when it is Z, second possibility. Now, if you consider this above the plane, below the plane, total 4 possibilities you can get. This is below the plane, above the plane, below the plane, below the plane, above the plane, above the plane, above the plane, below the plane. So total 4. So here we are getting 3, here we are getting 4. So it is not 8, but -1, 7. So this is a very tricky question. If you simply, mostly JEE Advanced, you will not get very straightforward question. It will be always tricky. So when you are getting 8, just check all the molecules when there is any sigma plane present or not. Okay. So 7 will be the correct answer. List 1 contains reactions and list 2 contains major products. So from the first one, here we have tertiary butyl group, then ONA, and we have this one. Now here what will happen? This is sodium tertiary butoxide. Sometimes it is also written like this. Tertiary butoxide, O minus Na plus. So this is actually very good base, very strong base. So this base, it can remove HBr from this molecule and it can generate some CC double bond also. So one possibility you can get number 4 molecule. Okay, so is it the only possibility? No, that is not the only possibility. Another thing can also happen. If this that is this Br, if it is replaced by, see, if it is replaced by OH. So here all the reactions are given, because just to save time I have already deleted all this. So see, this is possibility where it is number 4, and when basically these two products will generate together. If this is base, then this base, it will capture hydrogen from this position. So when tertiary TBU minus is capturing this, basically what will be the fate of this part? This part will be now attached to H. So this is the fate of this molecule. So both will be generated together. Now from the second one, OMe treated with HBr, here what will happen? This OMe, it is replaced by Br. So it is simply a substitution reaction. So it is matching with 2. So P14Q2, then so option B, it is matching, but we'll also see the other two. In the third case, we have NaOMe. Now again, MEO minus is very good base. It will capture this beta hydrogen. Why I am saying beta? Because with respect to bromine, this is alpha, this is beta. When beta hydrogen is removed, that is beta elimination, you are getting a double bond. That means again it is matching with molecule 4. Only one CC double bond containing molecule is present here. So this is basically E2 elimination. Even if you don't know E2 or E1, it is fine. You just have to see whether it is elimination or not. So it is elimination. Okay. And then because OM is very strong base, it will prefer elimination reaction rather than substitution reaction. And in the last case, here we have again this very large group, and there is the same molecule as you can see in P, but we have simply MEBr. So here what will happen? This base, as if it is attacking at this carbon. So base I am writing in simple way. So if it is attacking at this carbon, that is this lone pair, then what will happen? Br will be removed as a living group. Okay, so byproduct will be NaBr, and as it is attacking here, you will be getting this type of ether. But this molecule, it is not used in any of these cases, because if you, there is only one possible reaction where you can draw this molecule, and that is from number 1. If you remove Na and Br, and then only this type of structure possible. But see, this is so highly, statically highly hindered. So even if it is formed, it will not be very stable. So that is why ultimately this we will reject. Okay. So 1 P is matching with 1 4, Q is matching with 2, R is matching with again the CC double bond, that means 4. So option B is the correct option. Okay. Among the following compounds, the most acidic. So we will draw number 1 is para-nitrophenol. That means you have phenol, para position 1O2. Then B molecule is para-hydroxybenzoic acid. Then we have ortho-hydroxybenzoic acid. And in the last one, again we have toluic acid. So here CO2H group, para position CH3. Now we know that because of steric inhibition of resonance, in short we call it SIR, whenever you will have any ortho-substituted benzoic acid, they are very strong acid. So that is the reason it will be the correct answer. And why it is so? It is the reason when there is ortho substitution because of steric inhibition, CO2H group, it will not be in the same plane with the benzene ring. And as a result, what will happen? Suppose when there is no ortho substitution, then CO2H group, it is in the same plane. And then this type of resonance is possible. And when this type of resonance is possible, the lone pair of this oxygen, it cannot take part in resonance with the double bond. Suppose for simply benzoic acid, what happens? This type of resonance is possible, and as a result you will be having some positive charge generated over this oxygen, and this hydrogen will be very acidic. But this is inhibited if CO is involved in resonance with the benzene rings double bond. Okay, so that is why for benzoic acid the expected acidity we can't see, but when CO2H group is having some ortho substitution, then what happens? It becomes out of the plane, and the resonance with the double bonds of benzene ring not possible. So you can now have this type of resonance. As a result, this H becomes very acidic. Another way you can explain, if you consider its conjugate base, now it is O minus, and it can be stabilized by hydrogen bonding with this H at ortho position. So that is, these two are the reasons why this molecule will be having maximum acidity. Okay, option C is the correct option. And nitrophenol, obviously, compared to H group, CO2H is more acidic, so option A cannot be correct. Okay. So we are ending the session here. Thank you for listening.